So today's topic is dispersion. So what is a dispersion? So the dispersion actually has to do with the hypothesis, which was called H6. So that was a long way approximation. Long way approximation, and so essentially the idea was that to consider the limit in which all changes in space and also of u both in space and in time are large. So larger than any characteristic length that you have in the system physically. So the reason, so when the change is very large, the derivatives are small. Second derivative are even smaller. Third derivative are even smaller. So the use of this hypothesis was to keep only lowest order derivatives. Lowest order derivatives. Because higher order derivatives are large, are very small. So the dispersion has to do with the situation when this hypothesis is not anymore true. So essentially the idea of all these lectures that we have is that we started with wave equations that satisfies set of hypotheses, and whenever one of the hypotheses is not true or weakly violated, you have associated physical effect. So essentially to removing every hypothesis, you have a very interesting physical effects, and I'm only giving several of them which are most basic. But in fact, every hypothesis, so remember removing time irreversibility, we had dissipation. Removing small oscillations, we had nonlinear effects. So now removing the long wave approximation, we'll have dispersion. So actually you can keep doing this with the other hypothesis. So let's see what happens with H6, with removing long wave approximation. So that means that if it's not true that we must keep all order derivatives. So in other words, our equation equation of motion has to be the C20 to 2 to t square plus C0 to x square plus C40. I will write few of them so it will be clear what. And so on equals 0. So this is a general equation. We keep all the derivatives, but remember the derivatives are only even order because we still have this symmetry of space and time. So changing sign of space and changing sign of x and changing time of t should give the same equation. So only even order derivatives enter, but all of them. Yeah? So in other words, so what to do with this equation? So that's kind of a general equation when we remove long wave approximation. So how you solve it? So this is linear equation. So this is linear equation with real coefficients. And remember, whenever we have linear equation with real coefficients, we can use, it always implies that we can use complex solutions. Which immediately, taking real part and imaginary part, give us the two different real solutions. So whenever we have a complex valued solution, so U is complex, so we can consider U a complex, then so whenever U of xt, which is complex valued solution, we immediately have solutions, real solutions, which is just real part of uxt and imaginary part of uxt. So that's trick we already used many times for in the theory of oscillations. Here it's just used in the same way. So the complex form solutions are much more convenient. So we work with complex values of u, but we always keep in mind that actually on the real part makes sense, or imaginary part makes sense. So because physically u is a real variable, so going to complex variables is just a mathematical trick. And so what we do, we consider the particular solutions of the form u equal exponent I kx minus omega t. So whenever you write this expression, so the k is called. So in other words, so this, if you take real part of u, this will be cosine, right? So cosine kx minus omega t. So that's form of the solution we look at, and then it's periodic in x, periodic in time. So the prefactor of the space period variable is called wave number. So the wavelength, which is so wave number. So if you consider u as a function of x, then you know that the wavelength is 2 pi over k, right? So wave number gives you wavelength. Inverse of wave number by 2 pi gives you the wavelength. And the same similar way, the omega is called frequency or angular frequency. So in a similar way, u as a function of time is a periodic function, and the period is 2 pi over omega. So that's how you relate space and time dependence in this solution. So what we consider this kind of solution is just try to find k and omega which satisfy the equation of motion. So what you put, so what you immediately can see, that's every second derivative with respect to time. When you take it from exponent, it gives you minus I omega squared, right? Minus by minus give plus, I by I give minus omega squared. So it's every second derivative gives you minus omega squared. And every second derivative in space gives you minus k squared. Right? So essentially, every second derivative you substitute by minus omega squared. Every second derivative of x you substitute by minus k squared. So that gives you equation which is c to 0 minus omega squared plus c0 to minus k squared plus c for 0 minus omega squared squared plus c2 to minus omega squared minus k squared, and so on, equals 0. So that's how you translate this equation into equation between k and omega. And now you see that that's actually the left-hand side is just function of omega squared and k squared. So you can in the general form of this left-hand side is that there is a function which depends on k squared, omega squared equals 0. So that's a general form of this function. No, let's put f capital, small f. Okay, so that's just gives you a functional relation between k squared and omega squared. And then you can assume that it can be solved. We assume that it can be solved with respect to, so it's just a scalar equation, so you can solve it with respect to one of the variables. In principle, there can be many solutions, but in many physical situations, it's just one solution. So we assume that it can be solved. Okay. We assume that it can be solved. And then if f of k squared is negative, right, then omega can be plus minus I sigma, where this sigma is square root of f k squared, like this, right? So if this f happens to be negative for some k, then omega is imaginary. But then u will be exponent of, you see what is I kx by exponent I omega t with minus. And this becomes I kx by exponent I with I cancel, so it becomes plus minus sigma t. And this, for one of the signs, it grows exponentially. Right, so we have an exponentially growing solution from, so for starting for this solution can be multiplied by arbitrary constant before. So we have a solution which starts with arbitrary small epsilon and grows exponentially to arbitrary large value. So this leads to instability. So instability we do not allow, because we have this hypothesis. One of the first hypotheses is that there should be no unstable solutions, which means that, in other words, that function f of k squared should be non-negative. So we have function should be non-negative. And if function is non-negative, we can take square root. So we find that omega is a certain function of positive function. We take it non-negative, no? of k. Okay. So we can take always the square root. Let's not do this. Okay. So that's called dispersion relation. So in general, we have a family of solutions which are valid for all k or for certain range of k's, so wavelengths. And for each k, we give each k gives you uniquely the frequency omega. Right? So what is the graph of this solution? So the graph of this solution. So now remember that this is it. So let's just see how this solution behaves. So if we take u as a function of x, then it becomes some cosine. So this is cosine kx minus omega t. So which you can write like cosine k, and then remove x. X minus omega divided by k t. So you see that the form of this function is just a cosine, but it's, as time changing, it is moving to the right with the speed omega divided by k. See, so as time changes, it just shifts the variable x by the omega kt. So it means that it just move the same shape is moving with a constant speed, and this gives you the first notion of the phase speed. So phase speed is function of wave number, and it's frequency divided by wave number. So just exactly this. So this is a speed of motion of a mode cosine k x minus omega t. So this is the cosine, and this is just the shape is moving with the phase speed. Why phase is because usually the angle is called phase. So if you just fix a point with a given phase, for example, fix a maximum, so, then you'll see the maximum will be moving with a phase speed, or any point with a given phase with a given angle will be just moving with translating with a phase speed in space. So that's an idea. So now what you can see is what means long wave. The long wave approximation. So at that moment we released long wave approximation. Now let's go back to long wave approximation and see how long wave approximation comes out from the dispersion relation. So what means long wave? Sorry. I'm sorry. Okay, so long wave approximation means the wave is long, right? So L is large. So mathematically, you take wavelengths and think that it's very, very large. So wavelength very large means wave number very small, right? So when wave number is very small, in that case, you should get the wave equation. Okay. So at small k, you should get wave equation, which means that again substituting this ansatz to the wave equation, what you get is that minus omega squared minus a squared minus k squared equals 0. So there will be cancellation of minuses, and this gives you omega squared equal a squared k squared, or omega equal ak. So in this limit, you should get this relation. So from how you get this relation from a general law, it just means that omega at 0 is 0, omega d omega dk at k equals 0 is a. So if you have these two conditions, then you can expand the dispersion relation in Taylor series. Right? This we called A. And this is exactly the relation that we have in long wave approximation. So essentially, long wave approximation is just obtained from a general dispersion relation by assuming that k is small And in our case, what we know that the wave speed or the sound speed turns out to be derivative of the frequency with respect to wave number at zero wave number. And also we know that the very, very large waves, they do not oscillate. So the frequency at so zero, the constant state does not oscillate because k equals 0 is just a constant state. Okay, so that's two relations. That's the relations that we know. So we know that in general we can have some dependence between wave number and frequency. It should start from 0. It starts with the inclination, which is where the coefficient is wave speed, but then something can happen. So it may become nonlinear. So essentially dispersion, the effect of dispersion is that is the deviation of the dispersion relation from the linear form. So if in the exact wave equation we have a linear, if we have some if the deviation the dependence is non-linear, this means we say that there is dispersion in the system, right? So that's an idea. So now let's see what dispersion gives at all. So why is this important? To see what the so what do we have? So we have a collection of different solutions. All of them have a form of cosine, and all of them move with phase speed. So essentially, deviation of omega k deviation for omega from linear from linearization means that deviation of let's repeat it. So let's rephrase it. The dispersion is a deviation. You can also say that the deviation of the phase speed from constant. Yeah. So if we have a linear relation, then the phase speed would be, which is so if omega is ak, then the ratio is just a. So if there's no dispersion, the phase all modes with all wave numbers, they move with the same speed, and dispersion means that different modes, different k, they'll just move different speeds. So if you start with a linear combination of different cosines, they will kind of move differently. So what does it mean exactly? So let's consider a linear combination of two modes. So two different k. So because since this equation is linear, so any linear combination is a solution. So we get solution which is cosine k1 x minus omega 1 t. And let's take another one. So with coefficients 1, just exactly a combination of these two solutions. So okay. So this is a solution. So whenever each of them is a solution, it is solution. So what we have here is that omega 1 is frequency corresponding to K1, and omega 2 is a frequency corresponding to K2. Good. Okay, you can add this to cosines. Remember, so when you add the cosines, it's 2 times cosine of the difference by cosine of the sum times cosine of the difference. So that's trigonometric relation. So we start with the sum by 2, right? So half difference, half sum. And we subtract K2 from K1. Correct, no? This is exact. So now let's assume that K1 is close to K2. So the 2 K's are close, which means that 2 omegas are also close if the dispersion relation is continuous, which is usually the case. So what we do, so what means they close? So what we take K1 to be, so we say that K without index is a mean value, so the K1 will be K minus delta, and K2 will be K plus delta, and delta is small. Delta is small. Good. So now we will compute frequencies. So first frequency omega 1. So it's omega of at K1. Omega at K1 we can write as a frequency at K minus delta. And this expression we expand in Taylor. We take Taylor series of this expression around K. So it's like omega K d omega dk at value K with a minus delta and small order terms. Okay, this is for the first. For the second, it's the same function at K2. So we take it as K plus delta, take a Taylor expansion, and now it will be the same term, but with plus. So you substitute this into the expression, and you get that U, our solution is, so the 2 times cosine. So in the first, we take a sum of the two. Sum of the K1 plus K2. K1 plus K2 divided by 2 is just K. So it's Kx. And then minus half mean of these two values, so it will be omega. Sum of the first order term cancel, and then there will be just small term. So that's first cosine. And the second cosine, so let's put it more compact. Save space. And the second cosine will be about the difference. So the difference, half difference between the, so you take K2 minus K1 divided by 2. It will give the delta. And then it will be minus, and then taking the difference and divide by 2, it gives you derivative. delta t. Like this. Is good? Okay, so now the next step is we just neglect small terms, assuming that delta is small. And whenever you neglect small terms, so you get expression which is, first you get just pure cosine. And and next you also have a cosine, and here what we do, we take delta out of the parentheses. And we can do the same here. So what essentially what we can do is we can take k out of the parentheses. So you see that the two cosines are similar. One is multiplied by k, another by delta, and then x minus something t, x minus something t. So now this value we already know. So this is phase speed. It's phase speed. And then we have another similar quantity, which is derivative. And we will, so this phase speed is function of k, just to remember. So we introduce another quantity which we'll call group speed, which is this derivative. So, and we call it group speed. So you see, you in principle define two speeds. One is just ratio, another derivative. And there is a difference between two, of course. So graphically, whenever you have a dispersion relation, and you take any value of k, so the coefficient of the line which connects 0 with this value will give you correspond to the phase speed, right? So the omega divided by k. But the group speed will correspond to the derivative, to the tangent. So this gives you group speed. That's a difference. So either the coefficient of the prefactor of the line connecting to 0, or the prefactor of the line which is tangent to the dispersion relation. So now why is it phase speed? Why the other is a group speed? So we can plot this function. So what it is? So what you can see is that the first cosine is a fast function. So this is let's say the change. So you have to compare the two arguments. So and you can see that in the arguments are very similar. So at least in x dependence, so one is x multiplied by the k, another is x multiplied by delta, and we know that we assume that delta is much smaller than k. It means that since delta is very small, the argument of this cosine will change slowly, and argument of this cosine will change fast. Yeah, just because prefactors are very different. So we can plot the graph. So the graph is that the first cosine will give us fast oscillation, and the second cosine will give you some slow change. So we start with the second cosine, So this will be slow change. So that's what I plotted is a 2 times cosine delta x minus. Well, let's rewrite the function. So we have u xt equal to cosines, and I will put first the z cosine delta x minus group speed t, and another cosine k x minus phase speed t. So first we'll draw this cosine, which is slow. That comes from value 2 to minus 2. And this is with plus, and then we also plot the other with minus. And now we know that this cosine multiplied by another cosine, which is changing fast. So the product cannot go outside this what's called envelope. So the other cosine will just give you the other cosine will oscillate much faster, but it will be limited by this envelope. So that's a solution that we have at given fixed moment of time. So now let's see how it changes in time. So and it changes in time with 2 speeds. So there are 2 speeds involved. So one speed corresponds to the change of the slow envelope. So this group speed will correspond to the change of this. The whole envelope moves with a group speed, right? Because this function, as time is changing, it moves in space with Vg, group speed. While this function will move, the fast oscillation function will move with phase speed. So it means that the cosine which is inside, so essentially this every maximum minimum, will move with phase speed. So there will be motion which is composed of 2 different speeds. So there will be general envelope which is moving with 1 speed, and then there will be internal oscillation which is moving in another speed. And they have to be kind of in agreement between each other. It's good to, let's show it on the video first. And then Okay. So that's. Let's see how we do it. So that's exactly the solution we have. So what you see is that there are two speeds here. One is the envelope, and the speed of the envelope you can more or less follow by looking at the green spots. The green spots is the point in the middle. So the point in the middle, it moves with the group speed because it defines the speed of the full envelope with which the full envelope is moving. And then there is another speed of how the waves are moving inside, and this can be tracked with by looking at a certain phase. So keeping with a certain phase, for example, the maximum. So you're looking at the maximum, you see that this is a red spot, and you see that it moves faster than the red point. So there are two different speeds. And this is a general property of systems. And now we will see that it's actually more general than the just sine and cosine. So it's actually any wave train that you take around certain with a certain wave number. So if you take certain wave number which is modulated by another function, slowly modulated by a function, it will have two speeds. One will correspond to the motion of the full wave packet. So the envelope will move with one speed, which will be the group speed, and we will show that another speed, which is the speed just of given phase. So these two speeds are different. So here you can also see. So look at the maximum. You see it as the wave packet passed from left to the right. The maximum which was on the left, at the end which is already on the right. So there are two different speeds here. So let's make this derivation. So let's consider wave packet. So graphically, what wave packet is the solution which is modulated by a certain function. And inside this function, we have something which is close to the function with this, looking like a cosine multiplied by the envelope. So essentially, it's something like j of x by cosine kx, where this is slow and this is relatively fast. So the product of the envelope, slow envelope, and fast modulation of the oscillation. So this is the function u is what's shown here in red. So this is function u, and the white curve is just envelope, which is just showing the more or less the overall shape of the signal. Okay, so how you can write equation for this type of for this type of solution? In fact, let's show that you can extract this. You can represent this solution as So see, what you did there, we considered two modes, which is sum of the two cosines of nearby frequencies. Cosine is obtained as a real part of the exponent, so we keep it in complex form. And we can take cosine. So if we take a complex real part, so we can just put exponent here. And with kx minus omega t. Omega depends on k. So this is our cosine kx minus omega t. A real part gives you cosine. And now, in the previous example, we just took two cosines for nearby k's. But in general, we can take different cosines for different nearby k's. So we take put a coefficient which depends on k. In that case, it was just two coefficients for k1 and another coefficient for k2. But we can take different coefficients depending on k. And since k is a real variable, so we can also just integrate it. So that's still a solution. So first, what you can say about this expression is it's still a solution because every exponent is a solution. And any linear combination which is also a solution. And integral is a limit of this linear combination. So this is a solution. The next, if we want to have a packet, so what we want that all of them correspond to k. So we want that all of them. So ck should be is concentrated near some value k equal k0. So what it means that whenever we have a function c, which in principle complex, but let's just draw it as it was real. So it means that ck is only non-zero near certain value k0. So if the ck is concentrated near k0, so all exponent will have wave number close to k0. So this is a direct analog of what we had before with two cosines. So all k's should be close to certain value. So it means that it's more or less c is more or less limited between two values, k0 plus delta and k0 minus delta. So let's show that whenever you have this ck and this function, you get something of this form. So let's just first verify that. We all know this is a solution. Let's verify that this has this shape. By the way, this is what's called Fourier integral. Generalization of Fourier series that we had before. I'm not giving details of this theory here. Okay, so what we do now? Okay, so let's first consider time equals 0. Time equals 0. So what? No, before taking time equals 0, so first what we should do, we have this omega k inside. Omega k inside, but it's multiplied by the function which is not 0 only near k0. So essentially you can close to k0. So we can make expansion of this function around k0. It will be omega 0, omega f of k0 plus derivative at k0 k minus k0. No. So we take k is always k0 plus delta, where delta is more or less between minus delta and plus delta. So that's that case that we enter in our game. So because C is only defined for k between C is essentially 0 between minus delta and plus delta. Approximately. And then we can compute omega of that k, which is omega at k0 plus delta, and this can be expanded in Taylor series. This is approximately omega at k0 plus group speed at k0. And let's write it. Yeah. This can be written as k0 times phase speed, and this can be written as group speed. Okay. This is equal to that. This is equal to that. So this, remember that omega divided by k0 gives you phase speed, and derivative gives you group speed. Okay, good. So let's take initial time and see what is the form of our initial solution. So it's an integral. The integral, or no, real part of the integral. Ck. And now we can write k as k0 plus delta by the exponent, and then it's minus kx minus k, just minus kx, right? Because time is 0. So we don't even need to write it. Minus kx means it's minus k. Let's make more steps. So it's ck exponent I kx dx. And now let's write k in this sum. It will can be a real part, integral ck0 plus delta exponent I k0 x exponent I delta x. This is the k. And now we can integrate in k0 is constant, so instead of integrating in k, we can integrate in delta. And this integral is more now in delta is between plus delta, capital delta minus capital delta. Because in this region where c is changing. Okay, so this is constant, does not depend on delta, so we can remove it from the integral. And now we call this function, which is generally complex, so we call this function g of x is absolute value, and then phi of x its phase. So this becomes a real part of g of x exponent I k0 x plus phi of x. So our final expression so our final expression of u at x at time 0 is taking a real part, cosine kx q of x. So what we should say is that when we defined g of x, the x in this function only enter multiplied by delta. So these functions will be slow. They're slowly changing because they only change when with respect when delta x is changing, but delta is very small, so it will be changing slowly. So in order to have any change of this integral, x should change at least in such a number so that product with delta x is large. Yeah? A delta is small, so that means that this is slowly changing function, which means that the form of this solution is just this slowly changing function j, which is obtained through this integral. So having different coefficients function, you have different functions j. So we can also plot minus j. So j gives us an envelope. And then cosine k plus slowly changing phase give us actually the shape of oscillating shape of the solution. So that's our initial condition. So this is really, we see that taking this integral, we have something in the form of the pulse where the envelope is given through such an integral. And you can more or less, so what you see that this function is changing more or less and the distances, which is of order 1 over delta. So when the wave number is, or wavelength is order 1 over k, the side of envelope is 1 over delta, and delta is much smaller, which means that the envelope is much wider than the oscillation of the cosine. Okay, so that's initial condition. So the next is we have to compute what happens at t positive. What happens at t positive is just the same story. So now we take u xt. It's this integral. Now we keep the full integral. So next we we substitute k from that form. C k0 plus delta, exponent I k0x plus delta x minus, and we use expansion for omega, minus k0 phase speed t minus group speed delta t, and small correction is all integrated in delta. So the same as here, but we also keep the omega term. So this is term is omega kt. We substitute omega kt from the expression that we use here. Yeah, is it correct? Yeah. Okay, so now we neglect small corrections. So we say this is approximately real part. And then you see this exponent does not depend on delta, and this exponent does not depend on delta. So we can put them out of the integration. And what you get here is I k0 can be taken out of the parentheses, x minus vft. So taking these two exponents out, and then what will be inside will be c k0 plus delta. Exponent I delta x minus vgt d delta. So coefficient delta x vg t delta. Okay. And this, we know what it is, because remember that we defined gx minus phi of x as this expression. But the only difference between this expression and the expression that we have there is instead of x, there is x minus vgt. So this is by definition jx minus vgt by exponent I phi x minus v. Just the same integral, but substituting x by the x minus group phi t. So in other words, u of xt is approximately a real part of the exponent of g of x minus v gt by exponent I k0 x minus or vft t. And then there is also plus I phi minus vgt. This is f, this is g. Okay. And then we take a real part. By cosine. So what's the graph of this function? At t positive. So let's fix some t positive. So the difference is that now the envelope, which is slow function, should be moved to the right by vgt. So envelope moved with speed of vg. And we multiplied by cosine, which is still cosine k0. So there is still modulation inside. These two functions, this is slow. This is slow. Slow in x, right? And this is fast. So what you see is that you see that envelope moving with the group speed, while the phases of the cosine move with the envelope moves with the group speed, phases move with the phase speed. So there again, there are two speeds. The full envelope goes with group speed, but the phases go with the phase speed. So there are two speeds involved, and this is the graph that this is a simulation that we already saw on the video. Yes.
Nesse caso, tem dentro da fase do cosseno também tem termo dependente da.
Tem termo, tem também esse termo que, mas que muda a fase um pouco. Mas você tem que lembrar que essa função é lenta. Então ela realmente modifica. So this is slow phase. So not only the envelope is slowly the G slowly modulating the amplitude, but there is also slow modulation of the phase. This is true, which you I think don't see by the bare eye because main change is given by the first term, which is fast. So this is changing fast with x, and this is changing very slowly with x. So essentially, there are two effects. One is that which you see very clearly because this is amplitude. Another which you see, which is much less seen, is modulation of the phase. So there are two indeed. Usually, this can be disconsidered in the first order approximation because this is most important. And this is also important because it gives you the phase. Okay, so let's make a short break, really, because we need a lot of things to break. Till very short break, so it's 11:20, because we have a lot of things to finish. And I'll just prepare. Okay, so let's continue. So what we now know is that whenever you have some wave which can be somehow modulated in any way, the piece of the wave which has certain wave number close k0, it will have two speeds. One speed will be from the envelope, which is the group speed. It's a group speed which corresponds to that given mean value of the wave number. And then there will be another speed which corresponds just to phases. So the maxima minima. So this will be phase speed at that what's called the wave number, the mean wave number of the piece of this signal, or this wave. Okay, so let's see some. Now I will show you some application where you can see how it works, and especially we will consider the waves, surface waves, for deep water. So remember that we considered, before we considered the waves on a, so essentially what we had, so when the water was shallow, so the height was small. Remember that I told you that the wave speed was square root of gh. Right? So so it turns out then when the water becomes deep, so the height is much bigger than the water period. In that case, what it means that omega is approximately square root of GHK, right? So linear relation. In that case, for deep water, what you can get is that omega is, it should be J over K. No? Yeah. It's approximately square root J. So this should be J divided by J. Okay. In that case, omega is approximately J by K. So you see that in other words, so what we have the for water, for very large waves, the dependence is linear, and then it becomes at very short wavelengths, when the very large wave number means short wavelengths. When the wavelength is shorter than the depth, it takes form of the square root. So that's a dispersion relation. So in the asymptotic limit, it's another it is expression. So that means in the deep water, the phase speed is square root of jk divided by k, which is square root of j divided by k. So this is phase speed, and group speed, which is d omega dk, the derivative, and derivative gives you 1/2. So what is the important consequence is that phase speed is twice bigger than the group speed. Phase speed is twice bigger than the group speed. So it means that in deep water, the maxima minima, they move faster than the full envelope, twice faster. And I would like to show you some video first, and then we will go to the application. So this is a video of, so let's first see it. So when you froze, you can see this difference between waves, group speed and phase speed when you froze a stone in water. So this is deep water, so the wavelength is much smaller than the depth. And let's try to understand what happens. So I'll make it slow motion. You will see it several times. So first of all, you see the dispersion relation. The dispersion relation gives you that wave speed is, I removed it. So the phase speed is square root of j over k. So larger wave number, smaller the phase speed. So it means that the longer waves propagate faster. And this you can see very clearly here, that whenever you throw the stone, what happens that from the first disturbance, it splits into the waves, and the longer wave, it propagates faster. So after a certain moment, you see that the longest phase of waves are the first, then the shorter wave, then the shorter wave, then the shorter wave, and the shorter wave. Just this is exactly dispersion relation, that longer the wave, faster it propagates. So that's directly just already shows that there is a dispersion, that there is a different wavelengths, they propagate with different speeds. But at the same time, you can see that if you put some attention, you can see that there is a difference between the wave speed and group speed. So how we will do it? I'll stop it. So what we will do, I'll take a look at certain wave which is, make it. So I'll take a look at the wave which is kind of goes behind, and let's look at the top of this wave. So let's see where the wave. So wave was inside, right? So wave was inside, and we'll see that the phase speed bigger than the group speed means that this top of that oscillation will be moving faster than the group, the whole wave packet. So it means that at a certain moment it will just get to the end and disappear. So let's see that it really happens. So you look at one of the waves, and actually you will see that it comes to the end and disappears. So this is directly the. So on the same picture we see that there is dispersion because different wave lengths they move differently. The longer the wave, faster it moves. But also we can see the group speed. So that the region where the wave is contained is expanding slower than the motion of each particular oscillation. So the application that I would like to show you has to do with the wave which you see beyond the ship. So this is when the ship moves, you see the wave that he leaves behind. And somehow, if you look at this many times, you will see that actually the shape of this wave is always the same. It doesn't depend, the geometry of this wave behind the ship is always the same, whether the ship is small, ship is large, whether the ship is moving slowly or fast. It's only important that ship just moves with a constant speed along the straight line. To see that, just to see the difference, for example, you can see instead of the ship, you can see the duck. Also the similar pattern of the ship. Of course, size is different, speed is different, but in fact, if you superimpose, you will see that actually the intensity is different, but the geometry is the same. So let's just show that this geometry is direct consequence of the dispersion. So we'll just compute this geometry. Try to compute it on the blackboard. So we will derive, we will obtain the geometry. We will look for the geometry of waves behind the ship. You can always find it by the name of Kelvin ship wake. It was explained first by the Kelvin. And our analysis will be based just on three hypotheses. First hypothesis, which was first relation that we will use, is that relation. So all what we will need is that there is a dispersion in such a way that the phase speed is twice group speed. That's all. That's all what we need, information that we need for the dispersion. That phase speed is twice group speed. The second hypothesis will be that the wave pattern is stationary. Stationary means that whenever you are sitting on a ship and looking at waves behind, they do not move. So when you, and this is you, so waves move in inertial reference frame, but if you sit on a ship and look behind, you will see that you're moving, but waves are just moving together with you. So there is no, from an observer which is sitting on a ship, there is no motion of the surface. And the third is that wave pattern is self-similar. So what it means? So in having the ship, this is a top view, which is moving. So the ship moves with a constant speed. the pattern of the waves is stationary. So it means that this pattern, which is you see behind, just moving together with the ship. Yes.
Disser que a velocidade do barco é igual à velocidade de fase.
No, a question that velocity of the ship will be equal to the phase speed of some k, because there is no unique phase speed here. There will be what you will see that there will be phase speed of all different wave numbers. So there will be the whole collection of wave speed will just depend on what wave number at every point. So there will be a spectrum of wave speed. There will be spectrum of group speeds. So remember, wave speed is square root of jk, and group speed is twice more, or half of it. So it's not single group phase speed, single group speed. It's spectrum of phase speeds depending on wavelengths, a spectrum of group speed depending on wavelengths. So and the single speed of the ship. So let's see how they can come into the agreement between each other under these three conditions: that there is a ratio of 2 between the two, that the pattern just moves together with the speed, with the ship, and the self-similarity means the following. Self-similarity means that whenever the observer which sits on the ship just look along the straight line in any direction, he will see all the waves intersecting at the same angle with the same wavelengths. So along any direction of the observation, you will see waves at the fixed wavelengths and a fixed angle. So this is self-similarity. This is, you can also check that sitting well, you can also observe, but here it's assumption, and this assumption, actually we'll see that this assumption just allows us to give a solution, so it's in agreement with all these behaviors that are governed by the dispersion. So this is our setup. So let's now show that under these conditions we can just uniquely reconstruct the full picture of waves. So this is a challenging thing. So this is a line of the motion of this of the ship. So let's assume the ship was at a certain moment in that position, and then it moved to that position. So he moved at distance v, that's right, dt. And now what we will do, we will consider certain angle. So we'll sit on the ship and we'll look at certain angle. I'm better in drawing straight lines like this. So this angle will be, how I call it, psi. So psi is the angle of our observation. So after we moved the angle, we keep looking in that direction. Okay. Okay, so now let's look at certain specific waves. So let us assume that we have a piece of wave which is I plot it in a different way, no? Oh, no, this is okay. So wave will be at certain. So this will be wave crest. So this is a wave, and it's has a normal direction. So this is and this is a wave. Wave is always moving in the normal direction to the crest. So what we define is that we define this vector, this angle, we call it theta. So the theta defines the orientation of the wave that we see at that point. Okay, so then what we know is that whenever we moved, we still have the same wave here, right? Because nothing changed. So this wave has to move to that position. And we consider everything here is small, so you can consider that the wave is straight. It means that this point of the crest of the wave had to arrive to that point, to that point, which means that this distance is Vf k dt, because crest of the wave moves with the phase speed. Okay, at the same time, this point is already at a different direction, the different angle. So what we know is that wave number, the waves of certain wave number k are all along the straight line. So the waves at the same wave number k will be at that line. So the envelope should move just to here. So the envelope of a certain wave number have to move to that point. So that means that this should be group speed dt, because the given wave number just moves with the group speed, but crest moves with the phase speed. So now, and actually that's it. So now let's just rewrite this triangular and make an analysis. So we have a point A, which is this. A, let's call it A, B, C, D. So A, B, this is psi. This is theta. This is C. This is D. And oh, sorry. No, this is. So what is important to say? This was a normal. This was a 90 degrees angle, so this is also 90 degrees, right? C por B. Yeah. So let's just draw. It should be. This angle is the same as this. This is psi. So A, C, B, D. And we know that AC is VDT. We know that, so what we have, AC, side AC is VDT is how the distance made by the ship. Now AB is the distance made by the crest, so AB is phase speed dt. And AD is a group speed, is the distance made by the wave train of certain wave number. That's it. So that's our setup. So the rest is just analysis of this triangle. Okay, so what we do, so let's take that ADC triangular and use the sine rule. So the side divided by sine equal to the any side divided by sine. So any side divided by sine of the angle which is in front of it is the same for all angles. So what we can say that sine of this angle, which is pi minus theta minus psi, divided by AC, which is v dt, is the same as sine of this angle divided by the side AD, which is group speed dt. Okay. The next is the next is we take AB, this distance. We know it's VF dt. And also we can compute it as this side, this side of the triangle. Since this angle is 90 degrees, so we can find AB as V cosine theta. So dt you cancel, so you get Vf equal V cosine theta. And we know that Vg is half of, we know that group speed is a half of the phase speed. So we can just compute it as V over 2 cosine theta. So you substitute this to here, and you get that sine divided by pi minus theta minus psi divided by V equal, this will be sine psi divided by cosine theta, 2 goes on the top, and then there is V. V cancels. So we only have a relation between speeds, or between angles. Okay. The next is you open sine. So sine pi minus angle is the same as the sine of sum of the angles. And then you open it as a sine of sum. So what you get on the left, you get cosine psi sine theta plus sine theta cosine sine psi cosine theta equal to right hand side is the same. Okay, and that what you do, you multiply it by cosine theta divided by cosine psi. And what you get is that here this cosine will cancel. There will be sine cosine, cosine theta, sine theta in the first term. In the second term will be cosine theta squared by sine divided by cosine. It will be tangents. And then on the right hand side, this cancels, so it will be 2. Okay, and then you can split variables. You can expect tangent in terms of theta. Let's put it here. So you can express tangent of psi as some function of theta, where this function is, you see, it's cosine sine divided by 2 minus cosine theta, just expressing from that. And then we can open the, we can modify, we can express 1 as cosine squared plus sine squared. So it cancels the cosine. It will be 1 plus sine squared theta. It's just to see that the denominator is bigger than 1, between 1 and 2. Okay, so that's essentially it. So now we draw what this function is. So what you can see is that this function, so our interest is between the angles pi over 2 and minus pi over 2. So in both places, pi over 2 minus pi over 2, this is 0. Cosine is 0. And also it's 0 at 0. So there will be one branch positive, another branch negative. That's a drawing, and then it has a maximum and minimum. So the maximum occurs at certain theta star, and at certain tangent of theta star. So you can compute these two values. This is very rational. So the theta star is something close to 35 degrees, and then phi star is close to 19 degrees. Okay, that's it. So now let us go back to the picture. This is our ship. I will only draw the upper part of the waves because the lower part is symmetric. So what we have? We have theta, or psi. No, this is, psi is angle of our observation. So we see that the angle at which we observe can actually only change between 0 and 90 degrees. Because when angle is above 90 degrees, we don't have any solution. Yeah. So there is a critical angle which is 19 degrees. So the all interesting lines of our observation are, so nothing happens outside this angle. And we will see that it's really true. So no wave appears outside this part. And then there are what happens inside. So whenever you at 90 degrees, you have just single solution which correspond to theta star, and theta star is the angle of the normal to the wave. So there will be waves at this angle. So this angle of the so you see it's normal. So this angle is 35 degrees. This is normal. Okay, whenever you are inside, so small angles of observation give us two solutions, small and larger. So here you'll have one solution which is has a lower angle, another will have a larger angle. So and this will have this can be plotted at each point in exactly the same way. We don't know positions, but we know that there will be, we know angles. And then when we come to the straight line, which we go just behind the ship, the two solutions are 0 and pi over 2. So this is just 0 and pi over 2. So now you see that these are directions of the wave crests. So the wave crest will be the lines which at every point is tangent to one of these angles. And what you can see is that you either follow the angles which become lower, or you follow the angles which become steeper. So if you follow the angles which become steeper, you get the family of that curves. And if you follow the angles which become shallower, not very well. That one this direction. One direction is. So this is one direction, and this is another direction, right? So you get another family of curves which you can observe. So essentially, you have two different type of waves that are in agreement with our dispersion relation. One family of waves are corresponding to these curves which become horizontal, and another family is become transversal. And this geometry is a unique geometry that you can obtain, assuming that there is this ratio of 2 between the two phase speed and group speed, and assuming self-similarity and stationarity. Yeah, so that gives us a unique solution. And let's see that that's exactly the situation what we see behind the ship. So let's just return to our photograph. So the most difficult part is to understand this triangular. So usually you need several attempts to understand. So you should understand that the crest of the wave goes with a phase speed, but the place where the same wavelength is accumulated, it should move with a group speed. So now you can see maybe something which you didn't see before. So there are two types of waves always behind every shift. So one is a waves which become longitudinal, coming closer to the middle line. So this is one family of lines, and they all, first of all waves, they lie in the angles between 19 degrees up and down. There is no solution outside. And then there is one family of waves which just become longitudinal when they come to the center line. Another family of waves that you can see here that become transversal. And these families of waves, they meet at these lines. So they meet at this line. They have the same angle here, which is with the normal 35 degrees. So this geometry is unique. So what is changing between the ship to ship, one velocity, another velocity, or if you have a dark swimming, is intensity. The intensity we cannot get, because intensity depends on how much energy you put to each mode. So this essentially depends on the ship, but geometry is always the same. So sometimes the intensity is such that you only see these waves. Sometimes you only see these waves. But in general, all of them exist, just with some of them are stronger, some of them are weaker, but with exactly the same geometry. And the central reason for this geometry is a dispersion, so that there is a difference between the phase speed, which correspond to the motion of equal phases, and the group speed, which correspond to the motion of the full envelope. And what stays behind is the analytical relation that the frequency is non-linearly dependent on the wave number. Yeah. So just finalizing is that what you can conclude from these two pictures, well, yesterday's picture and today's picture. So yesterday we considered nonlinear effects. So nonlinear effect, what it does to any wave, it makes wave to it can start to break in the wave. It creates large derivatives. So dispersion, in some sense, works in the opposite direction. Dispersion wants to take a wave and kind of spread it, because it decomposes waves, a single wave, to different wave numbers, and every wave number goes to different speeds. So any disturbance that you started, you throw the stone, you get a disturbance, it will decompose to different waves, and they will go to different speeds. So at the end, they will just spread. So dispersion works, tries to spread the wave, while the nonlinearity tries to concentrate and break it. So then you can see that in principle, physically, both effects are always present. So you can imagine that the situation that if one acts against the other, so at certain situations then can come to the agreement. So they can compensate each other. And so tomorrow we will see directly the situation when the dispersion compensates nonlinearity and it creates a waves, special type of waves, exactly the waves that you see at the beach. Yeah, so that at certain distance from the beach. So okay. So tomorrow is the last lecture, right? And that's